So today we're going to start our study of differential equations, and there are a lot of different things that differential equations are used for, and we'll get a bit of a taste in terms of some of the applications of that as we go forward. But for now, a differential equation is just an equation that involves a derivative. So you'll have a derivative, and you'll see derivative symbols within that equation. Sometimes you'll see the derivative represented as a function on its own, something like this. So here I'm saying that the first derivative is represented by a function f, and that function doesn't have to be in terms of x, it might be in terms of x and y. So that's what this symbol is saying. The whole idea with solving a differential equation, as with solving an equation, is to find the values that make the equation true, balanced on both sides. And so for a differential equation, that means that we want to find a function whose derivatives make my original differential equation true. I have two examples here. In my first one, I have the first derivative equaling 2x. And so to solve that, what that means is that we want to find a function, y of x, so that the derivative of this function is equal to 2x. Well, that's a pretty straightforward one because through simple antidifferentiation, we know that x squared plus any constant, the derivative of this will in fact be 2x, and so that would satisfy that original differential equation. My second example, I have a second order differential equation. That just means that the greatest number of derivatives involved in this equation is a second derivative. And so the idea in solving this one is, again, we want to find a function y of x so that the second derivative of my function minus 6 times the first derivative of my function plus 8 times my original function is equal to 0. What function does that? Finding that is solving a differential equation. Just more precisely on this idea of a solution, we call our solution y equals y of x, our solution to the differential equation, on an open interval if the differential equation is satisfied identically on the interval when y and its derivatives are substituted. Just a couple of little things to notice here. First of all, the solution to a differential equation is a function, and that our solution has to be within an open interval, an open continuous interval. Now there are two types of solutions you can get when solving a differential equation. A general solution means that we have an arbitrary constant involved. This, for example, was a general solution to this differential equation because we can substitute any value of c, any constant of c, and the derivative of this will still satisfy this differential equation. When we actually find a particular value for c based on knowing a particular starting point in my situation, that's called finding a particular solution. So if we had been told in the case of this particular function that my initial condition, my starting value, my known piece of information was that when x was 1, y was 2, I would then be able to substitute into this general solution in order to come up with a particular solution for my differential equation. So a general solution provides a whole family of curves whose derivative is the original function. A particular solution is one particular curve whose derivative satisfies the original equation as well as the initial condition. So that's a lot of theory coming at you really quickly about differential equations. And just before I do some examples, just a couple of points to really emphasize based on what we've said so far. First of all, notice that the solution to a differential equation is always a function. We always need to keep that in mind when we're identifying our solution. And second of all, that the domain of the solution is a continuous interval that satisfies the differential equation. The solution is a continuous interval. We need to keep that in mind. Alright, so in terms of actually solving differential equations, there are lots of different ways out there for doing that. We're only going to look at one particular way in this course, and that's solving by separation. And solving by separation simply means getting all of the y terms on one side with respect to dy, and all of the x terms on the other side with respect to dx, and then integrating both sides. I'll demonstrate that with this example. We want to find the general solution of this differential equation. So I'm going to begin just by writing dy dx is 1 over x divided by x. And so to separate, like I said, we want to get something times dy and the other side something in terms of dx, so that all of the x's and all of the y's are on one side. So if I take this equation and I multiply both sides by dx, I'm going to get this. And this has perfectly been separated. Something dy equals something involving x times dx, because I can now integrate both sides. The idea is that once you've separated, you'll integrate both sides to obtain your solution. The integral of 1 dy would be y plus a constant. I'm just going to hold off on writing down the constant. On the right, the antiderivative of 1 over x would be ln absolute x plus a constant. And I'm going to put the constant just on one side because the constants from both sides can be combined to be a constant on one side, which is basically what I'm doing here. Alright, so you might say, well, there's the solution to my differential equation, but I got to keep in mind what I just said above about my solution being in a continuous interval. If I think about this function, let's just think about the picture of it. A y equals ln x graph, where x is positive, looks like this. And when x is negative, it looks like that. I can see that it's discontinuous at x equals 0. So my solution needs to be either on the right side or the left side, because my solution needs to be on a continuous interval. So there's a couple of ways I could write this. I could write this statement and I could say x is greater than 0, or I could say x is less than 0. Another way I could do it is I could break my absolute value up into its piecewise form. And so if x was positive, my solution would be ln x plus c, which you'll recognize as the right side of the graph. Or I could say my solution is the left-hand side, replacing this with negative x. So I say that my solution is either one of these two functions, or it's this piecewise function with one of these two restrictions. Okay? You can see why paying attention to the interval, the domain of the solution, is important. The domain must be on a continuous interval satisfying the differential equation. Now, if I was asked to find a particular solution for this differential equation, I would then have to choose which of the two sides I was going to take. So if I was told that my initial condition here is that the graph must pass through the point negative e comma 5, then I know that my point negative e comma 5 is about there. I'm dealing with my function on the left side of the graph. So to get the actual equation, I could take either of these two forms. If I took the absolute value form, there's my general solution. Let's substitute in my point to get my constant, to make it particular. ln of e we know is 1. And so the constant is 4. And so plugging this back in, I would say that my particular solution was y equals ln absolute value x plus 4, as long as x is a negative number, because my solution has to be on a continuous interval involving this point. Or I could have calculated my particular solution by simply taking the left branch, which is represented by that, plugging in my specific point, the negative of negative e is e. You can see that this is going to work out the same way. C is 4. And then by plugging back in, I could simply say y equals ln negative x plus 4. I wouldn't need a restriction since this function is self-restricting to be the left side. Let's look at another example. Let's find the general solution represented by y equals a function of y for this differential equation. So I'm going to take my equation and I'm going to separate x and y. I can do that by multiplying both sides by dx and by y, and that will lead me to y times dy equals negative x times dx. Once you have that, we can integrate both sides. The antiderivative of y is y squared over 2 plus a constant of integration, which I'm going to put on the other side. Antiderivative of negative x is this. And there's my constant of integration. I'm going to multiply both sides by 2. Two times a constant is another constant, so if you wanted to call that constant star, that's fine. And if we can, we want to isolate for y. And we can if we square root. But when we do that, we need to remember that the solution to a differential equation is always a function. What I have here is not a function. And so what I want to do is be clear about what my general solution is. It's either y equals the top part, the positive square root, or y equals the negative square root. It can only be one of those two because the solution to a differential equation is always a function. If I have a particular initial value to relate this to, as I do here, if x was equal to 1 and y was equal to negative 3, I would see that since my y values are coming out negative, that the branch that I need to use here is the negative square root branch. So this is my general solution for this situation. Let's apply the point to find the particular situation. X is 1, y is negative 3. Divide both sides by negative 1. Square both sides. And so my constant of integration is going to be 10. Substituting back means that my particular solution is the negative square root of 10 minus x squared.